Good morning. Good morning, everyone. Welcome to our virtual lecture. Today it's going to be a fairly short lecture, unlike the previous session we have had since the beginning of the semester. And I'm going to explain to you why. Welcome. We're going to start in a minute. Today is going to be a fairly short session on chapter 6. All right, we are still on chapter 6. Hope you are you're done with the two quizzes, quiz number 4 and quiz number 5. I will make quiz number 6 available before our midterm exam number 2. So today I want to get started from where we stopped last time, and this is a subtopic which is not new to everybody who has taken chemistry course before, and this is electron configuration. In introduction to chemistry, maybe you only learn about one method of writing electron configuration. I kind of like went through last time, all right, the first method, all right, and there is second method, and there is the third method, which you should be well-rounded in all the three methods of writing electron configuration of an atom or of any atom of an element on the periodic table, okay? Remember, chapter 6 is electronic structure of an atom. How are electrons arranged in an atom of any element on the periodic table? Is called electron configuration. Let me share my screen here. We are on section 6.8, writing electron configuration. There is what we call ground state. We're going to talk about the excited state. What is ground state electron configuration of an atom mean? It means arranging electron in such a way that they occupy orbitals orbitals with the lowest energy level. We say that is electron or ground state electron configuration. I don't think, let me see, I don't think you have this method in the text, which I, last time, I walked you through on how to write the electron configuration using this diagram. There is a diagram here, which I want you to learn, all right? I want you to learn how to come up with this diagram where you have our energy level 1, energy level 2, energy level 3, energy level 4, 5, 6, and 7, all right? And the number of sub-level or sub-shell within the shell number corresponds to the shell number. In other words, shell number 1 has 1 subshell. Shell number 2 has 2 subshells. Shell number 3 has 3 subshells. The 3S, 3P, and 3D. For fourth shell or fourth energy level, we have 4S and 4 of them. When we get to the fifth energy level, we have 5, 6, and so forth. Now you join, all right? You join the head and the arrow. Once you draw a diagonal arrow cutting across each subshell or subshells, you join the head and the what? And the tail of the arrow without lifting your hand off the paper, so that when you write the order in which subshell are occupied by electron, they will fall in the right place. I don't want you to, try to memorize this arrangement. I don't want you to, it will be too much, or chances are you may fail to capture the overlap of orbital. What do I mean by overlap? Sorry about that. I wanted to show you that if you try to memorize this pattern right here, chances are you may miss to capture the overlap. Overlap is having a higher value coming in before a lower value. This is called overlap of orbitals, and it has to do with the energy. It has to do with the energy. You interpret this as 6s being or having lower energy than 4f orbitals or subshell. Okay. So learn how to write this diagram, orbital filling diagram, so that when you are asked to write the electron configuration of any element, you reconcile the atomic number, the position on the periodic table, with the summation of the superscript number. You see this superscript on the PowerPoint slide on the right-hand side here, the superscript, these numbers, you should add all the numbers here until it corresponds to the atomic number of element on the periodic table. All right. If, for example, I'm looking for sodium, if we are talking about sodium, sodium is number 11. I don't expect you to memorize this. You'll be given the periodic table. I'll give you periodic table for that. I'll say, all right, 1s, all right, 2. I still need, all right, I still need 9 more. The next one after that is this, which is 2s, 2. The next one is 2p or 2p6. These are up to 10. 4 plus 2, 4 plus 6 is 10. For number 11, all right, for number 11, I need 3s1, 3s1. That is how you write the electron configuration, ground state. We're going to talk about excited state when we promote one electron to high energy level. This is one method of writing electron configuration. And for the other two methods, you need to understand this pattern. In order to understand the other two methods, you need to understand this main one. I call it method 1. And method 2 is orbital filling diagram, all right, where a box or a dash represent an orbital, all right, an orbital, of which this orbital, the definition of this orbital is, this is defined as a space in an atom where there is what? There is a high probability of finding electron or finding electrons. Where do you find electron? We call that orbital. And an orbital takes a maximum of 2. An orbital take a maximum of 2 electrons. You'll never see 3 electrons or 4 electrons in an atom. So I see this as an orbital, I see this as an orbital, I see that as an orbital, and can take up to 2 electrons with opposite spin. Remember we talk about the magnetic spin, they spin in opposite direction. So if you go back to the sodium, using an example to show you how you write the electron configuration, we assume that this was this, like 1s2, 2s2, 2p6, and 3s1. You should know how many orbitals are in p sublevel, d sublevel, there are 5, f sublevel, there are 7. They increase in odd number sequence. So this is 1s. And then you go to 2s. And then when you go to 2p, it is not one line. There are 3 orbitals. In everywhere you see p, you should always see 3 of them like that. This is an orbital. 3 of them. S, 3s. If you are going to 3s, there is only 1. And then 3p, has, all right, has 3 orbitals. If you want to continue, after 3p is 4s, like that, and then 3d, look at 3d. Everywhere you see D, you should have 5 orbitals. 1, 2, 3, 4, 5. All right. Anyway, you see B. So if I'm done with the B, you see here, when I'm done with the, from this, I'm done with the D, I go to 4S. When I'm done with this, you see this after 3D, you go to 4P. So from this pattern right here, you should know that next is 4B, and it has 3 orbitals. 3 orbitals. After 4B, what is the next sub-level? Right here, it is 5S and then 4D. So if I'm going to 5S, this will be my 5S, all right, and then forward 4D. I mean to say 4D, I should have enough space here for this is 4D, should be 4D, 4D here, and there should be 1, 2, 3, 4, 5. When you get to all right, when you get to F, wherever you see F, there should be 7 of them. All right, there should be 7 of them. This is the pattern. Where am I getting this? Let me go back again right here. You see, when we are done with the D, we go to 5, and there should be 6 of them. And then before we go to 6, so if I was to continue with that, I'll go to 5B, and it should have 3 like that. And then 6 S should be only 1. There is a pattern here you have to memorize. This is for orbital filling diagram, all right? So if I'm writing electron configuration for, you know, say hydrogen, which is atomic number 1 on the periodic table, it has only one, it has only one electron, and I'll show electron using an arrow. It can point downwards, or it can point up. When you go to helium, you cannot have 2 electrons pointing in the same direction. This is wrong. I know you say, I counted this 2, but you are violating Pauli's exclusion principle. They should have opposite spin, all right? They should have opposite spin. This is Pauli's exclusion principle, that when 2 electrons occupy the same orbital, they should have opposite spin. That is for helium. If it is for lithium number 3, I will add another electron for lithium number 3. For boron, number 4, is it boron? Number 4 is beryllium. All right, beryllium has 4 electrons, and this is the orbital filling diagram. Boron, I will have this. Now, when writing electron configuration orbital filling diagram, according to Hans rule, there was Pauli's exclusion. Hans rule talks about the degenerate orbital are singly occupied first. You may have forgotten about the Hans rule we talked about last time. Let me just go back to Hans rule. I think there was a Hans rule when electron occupy the lowest energy level. This is according to Hans rule, all right? We talk about Hans rule real quick. Yeah, I wanted to point out the Hans rule here, that when electrons, all right, when electrons are, when filling degenerate orbitals, the lowest energy are attained when the lowest energy is attained when the number of electrons having the same spin is maximized. So you should not pair them up. When I get to, that was boron, for carbon, you're just gonna put another one right there. Carbon, nitrogen, you see, I do not pair them up until they are singly occupied. You now start pairing them up when you get to atomic number. This is 1, 2, 3, 4, 5, 6, 7. Oxygen number 8 is when you will now come right here. Oxygen, that is how it is. And that is where you will see later on about 2 lone pairs. We're going to talk about the lone pairs when we get to Lewis structures. That is oxygen. Number 9, fluorine, opposite spin. Number 10, neon. All of them, they are paired up for neon group A. Group A. That is how you use orbital filling diagram. Number 11, sodium, which I was showing you here, will have 1 electron facing in that direction. The key thing is understanding how this pattern, this arrangement of orbitals, of which it is tailored to us. The first method, remember I had to go back to know which one is coming after the 4S, which one is coming after the 4D. It's not that you are done with the 4S, 4P, and then 4D, and then you say 5S, and then you say 5P, and then you say, no, it doesn't work like that. You don't say 3S, and then you go to 3P, and then you go to 3D, and then you come back to 4S, and then 4P. No, it doesn't work like that. You have to know this general or the first method right here, okay? And I cannot memorize this unless I know this. So all of them has to do with this first method. For you to really write this, so if I were you, I'll also master this. Once I know the first method, this one will be the template. I'll call this the template in orbital veiling diagram for writing electron configuration. So when you look at this, it's not about just memorizing and say, all right, let me memorize for nitrogen. Look at the nitrogen on the PowerPoint slide. It is 7. And then somebody will memorize and say, maybe the instructor will ask me a question on, no, it's just by knowing this pattern right here, and it will work for all elements on the periodic table, right? I'm not going to ask you about crazy one like number 118 on the periodic table. So long as you know the concept, for most element on the periodic table and how the pattern works, then you are fine you should be rounded in all the method of electron configuration. Don't rely on the fast method. This is what I call fast method. This is what I call the fast method, ground state. All right. This is orbital filling diagram. I will label it as method 2. If you don't separate the two, you may think that it means the same thing. No. On the PowerPoint slide here, I see 2 methods of writing electron configuration. And I'll just learn to reproduce this pattern right here so that when I'm asked, you should be able to answer the question. For example, I may ask you, which one of the following is the ground state electron configuration of, say, if you look at this, say nitrogen, one of the multiple choice might have 2 electrons paired up right here. If I pair these 2 electrons, somebody will just count and say, all right, it adds up to 7. That is not the criteria that, I should use the way we did in the first method. No. Sometimes somebody might trick you and start pairing them up. Remember, the generate orbital are singly occupied first before you start pairing them up, and it will just come out in the right place. Any question on the second method? I've walked you the first method. All right. And this is the second method. If I distinguish between the two, then you know which one is which. Any question on method 2 of writing electron configuration? Any question? If there's no question, and then I'll move on to the third, all right? I'll move on to the third method. I'll label this as the third, all right? I'll label this as the third method of writing electron configuration. This I call, is sometimes called the noble, all right, noble gas electron configuration, electron configuration. You know what noble gases are? They are which group on the periodic table are noble gases, if I may ask? Noble gases, you know where the noble gases are? Anybody out there? Noble gas on the periodic table? Group A, thank you, David. Group 8 are noble gases. So when this noble gas electron configuration, the first thing you should think of is group 8. What does it have to do with group 8? I know I've not talked about, you know, the core electron and valence electron. Some of you may understand what valence electrons are. All right, thank you, David. Yes, full electron, valence electron in the outermost shell. Electron in the highest n value, electrons in the highest n value are called, you know, valence electron. I'll come back to that later on, but let's just understand noble gas electron configuration. We use group 8 to indicate what we call core electrons, or electron are the inner electrons in electron configuration of an element. You may wonder, how will I know that these are the core electrons? Core electrons in electron configuration are represented using group 8 element. In that method, we use group 8 element too. All right, we use group 8 element to indicate or show the core electrons. Still using sodium, we have seen, all right, we have seen this before. All right, this is 1s2, 2s2, 2p6, and then 3s1. And then we have seen method 2, which is 1s with 2 electrons, 2s with the 2 electrons, and then 2p with all the electrons paired up. All right, all the electrons paired up, and then the 3s. This is the orbital filling diagram. For third method, which is the noble gas electron configuration, or shorthand, sometimes we call shorthand, you pick group 8, and I'm going to show you how you decide that. This will be the first 10 electrons. This is understood to have 10 electrons. Neon is number 10, and it will account for the first 10 electrons right here. These are the first, what, 10 electron, and then you indicate now 3s1. This is the third method now. This is the third method of writing electron configuration. This is where the group 8 comes in the third method. You use group 8 element to designate the core electron, So there is no way, all right, there is no way you can just write this unless you write the long method or method 1. The first one I'll show you, 1s1, 1s2, 2s2, 2p6, and so forth, in order to write the shorthand. We call this sometimes shorthand, all right? This sometimes we call this short, all right, shorthand, or abbreviated, because if you look at this, we don't indicate, you don't see electrons, you don't see the 10 electrons, but it is understood that there are 10 electrons, and we use parentheses to indicate those 10 electrons. How will you pick group 8 element? Let me just show you the criteria by which you pick an element. So let me just pick up periodic table here. Periodic table of elements. I'm just gonna pick any periodic table. Maybe just look at that. All right, let me just show you this. No, Yeah. Yeah, this is the periodic table. This is the periodic table. And using sodium, the one I just showed you, remember, I use neon number 10 to show the core electrons. In writing the shorthand electron configuration for sodium number 11 here, number 11 on the far left side on the screen, if you see this is sodium. In writing the shorthand or noble cast electron configuration, this is how you pick group 8 element. This is how you pick group 8 element. You look at look at the element in question. All right. In this case, this was an example of sodium. You call one row above that element, one row above that element, and then you go all the way to group 8. That will be your element in parentheses. That is the criteria by which you pick the element to put in parentheses to account for the core electrons. You cannot go two steps like sodium and then I go 1, 2, and then you go all the way to helium and then no, that's not how it works. It is one step back in terms of rows. So for rubidium number 7, I'll say, all right, that's 7. That means that 7 electrons. I'll go one step backward, row 4, go all the way to, you know, number 36. Krypton will take care of, look at, Krypton will take care of 36 electron. Let me show you, I'm gonna write this. I'm writing electron configuration for, all right, rubidium, number this, RP, this is number 37. The shorthand, I'm gonna put krypton in parentheses, and this will take, let me just get out of here. This is number 37, all right, this is number 37. This has 36 electrons. This has 36 electrons right there. And with the 36 electrons, how many do I still need to? I still need 1, but the challenge is, how will I know if it is 3D, if it is 5S1 or 4D1, which one, which sub-level? That will call for writing the long method of electron configuration, right here. Up to this point right here, this is 30. This has 30 electrons. And up to here, this has 36 electrons. So the next sub-level is 6s2, 6s2. And for 37, I need only 1. I need only 1. And this will be 6s1, 6s1. This has 36. This has 1. It has up to 37 electrons. I didn't have to memorize, you know, the electron configuration of rubidium. The criteria by which I picked krypton is looking at the position of rubidium, which is the element in question, go one step backward, go all the way to group 8, all right? How many or what is the atomic number of that element? That will account for the core electrons. We call these core electrons, It will account for 36. And then I need what? I need 1 more electron. There is no way you can just memorize and say 7s1 or 5s1 unless you go to the fast method. All right, how will I know that? You have to do the math and say, all right, okay, 36, all right, this is 30, 36. How many do I still need to 37? I need only 1 in 6s1, all right, and this is the third method of writing electron configuration of elements. So there is method 1. Look at my PowerPoint slides right here. This is method 1, the long one. And then method 2 is, you know, orbital filling diagram, and I walk you through that. And then we come now the shorthand, which is using the noble gas electron configuration. noble cast to show that I think we did this before. This was Hans rule, all right? The lowest orbital energy is reached when the number of electrons with the same spin is maximized. This is Hans rule. You may want to read more on these other guys. I don't want when I throw a question, give you all these personalities, you will not be able to tag what they did, all right? You'll not be able to answer a question. You may end up just guessing. So condensed or shorthand is just what I went through. Elements in the same group. Valence electrons, these are electrons in the outermost shell. Right here. Since we're going to talk about valence electron in chapters 7 and 8, valence electrons, all right? These are electrons in what? These are electrons in the outermost shell, or electron occupying the highest n value. You may say highest what? Highest electron in the highest n value, of which it's very easy for main group elements. Main group elements, the number of valence electrons corresponds to group number. Group 1, they have 1 valence electron. Group 2, they have 2 valence electrons, and so forth. We'll see in chapter 7. So valence shell contains valence electrons. These are group 1. And there is a reason why we say a main group elements on the periodic table. They are numbered with a letter and a number, where the A are the main group. For main group, all right, main group, all right, main group, valence electrons equals to what? Group number. So group 2A will have 2 valence electrons. Group 3A will have 3 valence electrons. Group 4A will have 4 valence electrons. Group 5A will have 5 valence electrons. 6A will have 6 valence electrons. 7, except in group 8, except helium. Helium is in group 8, and it has 2 valence electrons. But the rest will have 8. Just a simple way of, keeping track of valence electrons with respect to the group number, all right? With respect to the group number. The inner one we just call the core electrons, all right? In writing the condensed electron, we use the bracket to indicate the core electrons. And the valence electrons are those electrons which are not, which are not indicated. For example, here in this example I showed you before, 6s in 6s2 in 6s1. This is the valence electron. It's in group 1. In group 1. With that, that is just what you need to know as far as the 3 methods of writing electron configuration. I've seen question, all right? I've seen question where the answers could be all of the above, or 2 of the above, or maybe A and B. For example, I can give you, say, the ground state electron configuration of fluorine is which one here? Let's first of all answer this before I give you an example on situation where you have 2 answers being correct. Let's look at the PowerPoint slide, learning check. The ground state configuration of fluorine. In this example, you should be able to name the element on the periodic table and use the symbol to identify the position. Fluorine is number what? Fluorine is number 9 on the periodic table. This is fluorine. and its electron configuration is 1s2, 2s2, 2s2, and then 2p6, no, 2p5, not 6, 9 electrons. For shorthand, helium is the group 8, and it will take care of 2 electrons. So this will be 2s2 and 2p what? 2p5. This is how you go about answering a question along the condensed or shorthand. This is wrong. Don't just, unless you know what what the chemical symbol in the parentheses indicates, you will be double casing yourself with the valence electron. So I need to have, I think the correct answer here is D. That's how you use that elimination method. So back to where I was saying, you may have 2 possible answers. You may see this as A. This might be A in the exam, and this might be B, and then say 2 of the above, or A and B. You may have come across multiple choice where they give you that A and B are correct. So this is correct, and this is correct. All right. I may give you an electron configuration and say identify the element represented by the following electron configuration. You have to look at the periodic table and reconcile with that. Any question on the 3 methods of writing electron configuration? Any question? Transition metals, we just talk about the, the periodic table being main group elements. There's the D, or breaking down into the transition in a transition metal. These are the D block elements, where the subshell being filled is the D. If you look at the arrangement of subshells here, these are degenerate orbitals. These are degenerate orbitals. And if you write the shorthand electron configuration for manganese, you don't pair them up. It's understood that we have 18, 19, 20, 21, 22, 23, 24, 25 for manganese. For zinc number 30, it's the same way, all right? As we did before, you can be asked to write in any form. So argon number 18, to give you an example. Common mistake I see students making in transition metals is forgetting that 4S comes before 3D. Look at this, 4S comes before 3D. This is the energy level or sub-levels according to increase in energy. 2S is lower in energy than 2P, 3S is lower in energy than the 3P, 4S is lower than the in energy than the 3D. This is when we talk about the overlap, okay? There is the overlap. For lanthanide, it follows the same way, except that in this case, we now get into filling the F orbitals, and there are 7 of them. If it is 4F, you should understand that every F, where you have F subshell, you have 7 of them. 1, 2, 3, 4, 5, 6, and 7. All right. Anywhere you see F, all right, anywhere you see F, whether it is 5F, you should have 7 orbitals. 7 orbitals. All right. And you fill with the electrons as well. This just section 6.9 is just continuation of what we looked at, main groups and the inner transition, what sub-labels are. Element on the periodic table are grouped according to which sub-level is being filled by the last electron. Breaking down the periodic table into what we call the S plug element, the blue one, S plug element, the is it maroon or whatever the color it is, this is P plug element, D plug element, and F plug element. What does this mean? It means the last electron when you write electron configuration goes to what subshell? If it is D, we call that D plug elements and F plug elements. Question along this line is, which one of the following is a D plug element? You have to be able to break your periodic table into plugs: D plug elements, F plug elements, S plug element, and P plug element on those lines, so that you see which one belongs to different plugs according to the last electron. D is orange. Pink doesn't really look pink to me. This means the last electrons goes in the P plug element. Of course, I will not, as simple as you see on the PowerPoint slide here, I will not give you the periodic table, or you'll not see a question saying that, which region of the periodic table is the D plug element, or which one, or of, no. Here it's assumed that you can reconcile with the element on the periodic table. For example, which one of the following element is P plug element? Anything on the periodic table on this side, you know what they are, right? In order for you to answer the question on D plug elements and F plug elements. Now, to wrap up this chapter, anomalies. I know you may have think that that is easy, but there are some abnormalities. Let me call it abnormalities. That means it does not follow the regular pattern when you write electron configuration. For example, chromium is number 24. Let me just give you chromium. This is 24. You'll expect this to have 1s2, 2s2, that is 4, 2p6, that is 10, 3s2, that is 12, 3p6, that is 18, 4s2, that is 20, and then 3d4 to make it 24 on the periodic table. This is wrong right here. This is wrong. The correct answer is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. 3d5 is correct. You promote one electron from, from an inner subshell to the outermost for chromium. The other one is you'll expect copper, number 29. All right, if we write electron configuration 1s2, 2s2, 4, 2p6, 10, 3s2, 3p6, that's 18, 4s2, that is 20, and then 3d9. You expect that to be the right answer, but that is wrong. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. This is the correct electron configuration. Within the first 30 elements on the periodic table, among the first 30 elements on the periodic table, these are the two elements with abnormal. Some irregularities occur when there are enough electrons to half fill 3, the S and the D. If you look at the S and the D, it's just right here and right there. I'll just worry about the first, those two element on the first one. Of course, there are some other elements with the same abnormal on the periodic table. Chromium is an example. How will I know that this is what it is? If you have a D4 and a D9, this is D4 and D9 rule. If you write the way we normally write, or the ground state, how we learned in the first method, and you end up with the D4, you promote the electron on this sublevel, all right, into that subshell. If you look at this was D4, we made it to D5. That's correct. This was D9, and then we make it to 10. That way, it is more stable when it is, when it is half filled, when the D is half filled or fully, completely filled. This is D1. I didn't mean to say 2. This is 1. We have 1 right here. This is 1 right there. From 2 here to 1. When you add up, it's going to give you the electron. You're right, Antonio. Yes, it is 4s1. 4s1. Thank you. That is correct, Antonio. Antonio is correct. Is D4 and D9 is the criteria by which I will know that I need to promote what 1 electron over to see. There are just few elements, and as I say, on the periodic table, only chromium and copper. The first 30 elements, those are the only elements with abnormal or anomal electron configuration, so that when you look at chromium, you'll expect this, but we go to this because it was D4. I've seen that wherever I end up with D4, promoting 1 electron will work fine. The copper is another example. I don't want to go in details into the rest. All right, those are the abnormal. So I don't want, when you're given, be careful when you're dealing with abnormal. I will only want you to understand that among the first 30, copper and chromium are the exception. That marks the end of chapter 6, and I don't want to start chapter 7 today because of obvious reason. Let me show you where we are in terms of the lecture and the course syllabi. Today is based on the course outline. All right. If you look at the course outline, all right. If you look at the course outline, all right, right here. Today is June 25th, chapter 6. We are in good shape. And next week we should be starting chapter 6 and start 7. Since we are a little bit ahead of schedule, I will start chapter 7 next week. All right. Next week, Thursday, July the 22nd, just like midterm exam number 1, I will make exam number 2 available for 24 hours. It's going to be available for 24 hours. And quiz number 6 for chapter 6, I'll make it available by end of today or maybe early tomorrow to sometimes next week, because I want you to have, you know, a feel of what question will be in the exam, or, you know, if you have really mastered the concept, for example, of electron configuration. I don't want you to learn in the exam that, you know, oh, I had never seen a question on this. So I'll make chapter 6 homework available. Do some of that next week before we take the exam. I don't want you to, you know, to do the exam and then you go back and do the quiz. It should be do the homework, or even start reading fast, do the homework, do the quiz, and then do the exam, and then you improve gradually. And, you know, That way, you will be well-rounded to challenge the exam. Other than that, that marks the end of our lecture. I did post some some videos. It's not, it's just for practice. It's under my lab and mastering. It shows up like an assignment, but it's video animation. It's for you to learn out of them. Maybe you watch a short clip on some concept and you are asked a question. Those are not created. If you think that that is helpful, please let me know. I will make available more videos along those lines. That way you get more resources for you to learn, all right? Thank you. I'll see you next week. I'll stop now sharing my screen. Have a great day. Be safe. See you next time. Thank you.